Hello everyone. In today's session, we are going to explore one of the most important topics or the concept, that is the problem characteristics. So, before any AI agent can choose a search strategy, so it must first ask, so what kind of problem it is going to solve? Is it simple or complex? Is it predictable or uncertain? So, is there any possibility of doing mistakes? So, this is exactly what this session is about. So we look at the key characteristics that describes the nature of the AI problems. And we will try to understand how these characteristics determine which algorithms we use. Okay. So these, before going in and talking about the different characteristics, okay, these are the characteristics we're going to talk. So we have to understand why we go for a problem characteristics. So already we discussed the agent should know the nature of the problem before solving it. It's very, very important. Before he chooses an algorithm, he should try and understand what exactly the problem is. Because in the real world situation, all problems are not same. They are different. We cannot predict every problem. Okay. A medical diagnosis problem is different. A traffic signal problem is different. One is very complex. One is very dynamic. So, all these things the agent has to consider before he approaches to a solution. So, these are the problem characteristics we will study. So, we'll study in two parts. So, first part will have a few, and second part will have a few. So, the first one is the problem decomposable. So, first, before going in and approaching and trying to solve a problem, you have to think, can we break it into smaller independent parts? That's the first characteristics. Second is, can solution steps be ignored or undone? So what happens when we make a wrong move? So it's very important, right? Every time we cannot move in the right direction. Third one is the universe predictable? So does the environment behave consistently? Certain problems might be dynamic. Suppose if you are taking a traffic signal, a lot of uncertainty is involved in it. Okay. Fourth one, is a good solution absolute or relative? So, is there one best answer or is it good enough to accept? That also we have to check. Fifth one, is a solution a state or a path? What exactly are we searching for? It's very important. Right. Sixth one, what is the role of knowledge? So, how much of information does the agent really need to arrive at a solution? The last one, does a task require interaction with a person? Is there a human in the loop? So, all these things we will study in detail. We will see examples to understand all these things. The first question is the problem decomposable? Okay. So, a problem is decomposable. Okay. A problem is decomposable if you can break it into smaller independent sub problems. Okay. So, means we can try and solve each of the sub problems separately and then combine the results to get the full solution or the final answer. Okay, like we can take multiple examples. So, for example, suppose you're trying to solve a jigsaw puzzle. Okay, so each section of the problem or the puzzle can be assembled independently. Then that's the left side, the right side, the border. So you don't have to finish it one to start another. So you can do it separately. Okay. Then you can combine it. So we will take one classic example from this slide, that is a route planning from Chennai to Delhi. Okay. So you're going to start from Chennai to Delhi and you're going to go through Bangalore and Hyderabad. So how this problem of going from Chennai to Delhi can be decomposed, because our question itself is the problem decomposable. Okay. So we are trying to break down this complete journey into smaller decomposed parts, smaller routes otherwise. So we can break down as Chennai to Bangalore, then we can go Bangalore to Hyderabad, and then we can go to Hyderabad to Delhi. So our goal is start from Chennai, go to Delhi. So this is a simple example for a decomposable problem. So what is about non-decomposable problem? Non-decomposable problems are example that cannot be decomposed, right? So every move affects the future game. They're not independent. One move is dependent on the other. So you cannot solve one part of the board independently from the rest because everything is interconnected. Okay. So that is a uh, that is non-decomposable problems. Okay. So which we cannot say which board position is independent because all boards positions in the board are interconnected, so you cannot decompose that. Okay, now we can see in the above decomposable problem here, if you go from Chennai to Bangalore, this is one independent substitute. When I go to Bangalore to Hyderabad, this is independent. When I go from Hyderabad to Delhi, this is independent. So each part of the journey is planned separately. Okay. These are three smaller problems. So a problem is decomposable means we can decompose into independent subproblems. That's what is very, very important because this is independent, and this is independent. Okay. Now we will take a example. See, this is the same thing I've shown pictorially. Our point is from Chennai to Delhi. So I can go from Chennai to Bangalore. This is an independent problem. Then I can go from Bangalore to Hyderabad. Again, that is an independent problem. Then I can go from Hyderabad to Delhi. Again, that is an independent problem. The same thing I've shown it pictorially for you to understand. So this is a final decomposed part from Chennai to Delhi through three subroutes. Chennai to Bangalore to Hyderabad to Delhi. So this is a quite simple understanding to before an agent can solve, it has to understand whether the problem can be decomposed. That's very, very important. Okay. So we'll take an example. Same example. Okay. We are going to take up a code and then we'll try to see how an algorithm can be used in the same code. So that's what I'm going to talk about now. Okay, so first, algorithmically, we are going to see that's the point to understand here. So we have a road network because the last example was same. So I'm trying to continue with the same example. We have a road network represented as a graph. Okay, here cities are nodes and the roads are edges. Okay, now our goal is to find a path from Chennai to Delhi. Okay, right? Using algorithm breadth first search. We're trying to implement BFS here. Okay. So how does the BFS start working? It will go level by level. Already we have seen a lot of examples. So we start from the source city Chennai. Okay. Then we use queue to store the paths. Queue is a data structure. So we try and use a queue to store the intermediate parts. Okay. So we try and put the visited cities and mark them visited so that we don't revisit it again and again because there's no point in revisiting again and again. We even discussed the water jug problem that we have to try and avoid revisiting the states. Okay? So we keep something called as visited, and whichever city we have visited, we push that into that visited. Okay. Now we have to, I mean, we have to we'll go through how it happens. Okay. Right now we have seen here Chennai. You can go to Bangalore, Vellore. You can go to Bangalore again. Bangalore to Hyderabad to Chennai, Hyderabad to Delhi, Nagpur to Delhi, and this is the final destination. This is the road. The graph for you. Now the same thing. If you're going to represent this as a graph, you can draw the graph. So you can start from Chennai. You have two paths. That is, one is from Bangalore. See, suppose I'll just try and draw. This is Chennai. I'll put it as C. Drawing is very bad. You have two paths. One is Bangalore and another one is Vellore. Okay. So either again you have from Bangalore you can go to Hyderabad. Okay. Then from Hyderabad you have two parts. One is Bangalore, another one is Delhi. So my path may be Chennai to Bangalore, Bangalore to Hyderabad, Hyderabad to Delhi. So this is a kind of graph you can construct. Okay, right, right. This is a graph representation. Okay. Now, how does the BFS algorithm works? That's very important, right? So start from the source city. What is the source city here? The source city here we are taking is the we are going to take the source city as the Chennai. Okay, I'll just mark it as C. We'll take the source city as Chennai. So we pop Chennai, but it's not the destination. We pop Chennai. So we add it to the visited cities. Okay. And we try and enqueue its neighbors. Okay. So we suppose you are using queue now. I'll just check. Yeah, it's shown here. Okay. So what we try and do is we start from the source city Chennai, stores a path in the queue. So in the previous thing, Chennai, we have Bangalore and Vellore, right? Stores a path in the queue. So in my queue, you'll have Bangalore and Vellore. Okay. So visit cities level by level. So mark visited cities. Now I'll pop out Chennai. As I said earlier, I'll pop out Chennai because it is visited. Now we will try, this is my queue, right? So I will try to enqueue the neighboring cities. What is my neighboring cities? That is Bangalore. So likewise, in my queue, I'll have C. I'll start from C and then I'll go to B. Okay. Then again in this queue, I will try and add the neighbors of the Bangalore. What is the neighbor here? Hyderabad is the neighbor. So already in my queue, I have B and then I have H. Now I have to take out B. So likewise, this keeps on moving. Okay. So we'll take a code as the example and then we will try to do. Okay. Right. Here, as a code, if we write, I'll just try to use this. We have a queue. So we will create a queue and insert the starting city as the first path. So what is the starting city? Chennai is the starting city. So we will keep something called as visited and then we'll put it inside that. Okay. Then we will try and loop over and then we will try to solve the same problem. So what happened? We will say q dot pop left, meaning remove and retrieve the first path from the queue. What is in queue? In my queue, I have Chennai. So I will put it in the queue. Okay, then get the last city in the current path. What is the last city I visited? Because I have not explored any of the cities. So Chennai is the last. If I'm going to check if city is equal to n, if Chennai is equal to n, no, because our end is Delhi. So Chennai is equal to Delhi. No, it's not. It's false. Okay, right? If city is not in visited, process a city only if it has not been visited before. Now, if I have the neighbors of Chennai, what are the neighbors of Chennai, Bangalore and Hyderabad? So I will check if Bangalore and Hyderabad is not in the visited list. Then I will go and try and do the same process for Bangalore and Hyderabad. If it is already visited, for example, Chennai is already visited. If Chennai is not in visited, go and add it to the visited. Okay. Now, after that, we will try and get all the neighboring cities, that is Bangalore and Vellore. Then again, you repeat the same process until you get the best solution. Okay. So, BFS naturally tries and find out the shortest path. Okay. Here I have told the same thing for you step by step as a tabular column. Okay. So, our current city is Chennai. Initial, I've just written the same thing. In the whatever is the code, I've just put it in the tabular column for you to easily understand. So initialize the queue and the visited set. So queue after processing, initially it will be Chennai, right? First will be initially visited set will be 0 because we are only having in the queue currently visit current state is Chennai. Okay. Then after I add Chennai to the visited set, now in my queue I will have Bangalore and Vellore to the queue. Bangalore and Vellore will be added to my queue. Okay. Now, after that, I will, in my queue, we have Chennai and Bangalore. Current path I will, next is Bangalore. So my current city is Bangalore. So I will add Bangalore to the visited set. I will add a Hyderabad to the queue. Okay, I will add a Hyderabad to the queue. Now, what are the neighbors? Okay, okay, add Vellore. Next will be Vellore, right? Because Vellore is left. Vellore. So add Vellore to the visited. So try and find its neighbor, that is Bangalore. It's already visited. Then again, we will try to find the current city, that is a neighbor, that is Hyderabad. Okay. So add Hyderabad to the visited. So neighbors of Hyderabad are Delhi and Nagpur. So you will add that to the queue. You can see Nagpur and Delhi to the queue. Okay. Now, okay. So now we have already added Chennai, Bangalore, Vellore, Hyderabad. Okay. Now, current path removed is Chennai, Bangalore, Chennai. So now we have to find whether Chennai is already visited, so we ignore, and then we come to Bangalore, it's also visited, so we ignore, and then finally we had the Delhi portion. Delhi is the destination, and then that is just stopping, and then we are the path is Chennai, Bangalore, Vellore, and Hyderabad, and finally we'll go to Delhi. We'll add Delhi here. Okay, so this is how your queue works, right? So next we will take one more example, that is the Blocks World example. This is a very famous example, okay, and a beautiful example always. So we have three blocks here, A, B, and C. So initially C is on top of A and B is on the table. So what is our goal? Our goal is to start A should be at the bottom, B and C. So all should be stacked one after the other. That can be in any format, C, A, B, C, any form. So the agent, what is the role of the agent? Agent must try to plan a sequence. So suppose if this is your initial state, considering the same. So first, what we can try and do? Okay, so he can try to see. This was my previous. This is current state, right? So I can try and move the C onto the table. Okay, so move C onto the table. Now point here is then we can try and take B and put it on top of C. Then B is on top of us. Finally, what we can do, we have only A left out. Okay, so what we can try and do, we can take A and then we can put it on top of B. Now it is A, B, C. So when you're trying to solve it step by step and independently, steps can be broken down independently. So this is why the blocks world is a classical decomposable problem example. Okay. So now we will move on to the next concept or the next characteristics. Can the solution step be ignored or undone? So far we have been talking about problem decomposition. Okay. So this is the second major characteristic. What happens when we take a wrong step? Okay. So that is what we are going to talk about. Okay. What happens when we try and take a wrong step? So can we ignore it a certain step or can we undo it? Okay. So this is where we will talk about two more important properties. Okay, right? So this step will tell us whether the previous steps has to be remembered or can we reverse it, can we safely ignore it. All these can be discussed over here. So with this, we will talk about two characteristics, important key properties. One is ignorable versus recoverable. Okay, first we will talk about ignorable. What is meant by ignorable? Can a solution step be safely skipped? Means if a step is ignorable, if skipping a step, so if that step, skipping that step doesn't prevent us from reaching the goal, so it has no effect otherwise. Is it okay? So even skipping the step will reach us to the goal, then is it okay? Property to recoverable. If step is recoverable, or we can say, can the solution steps be undone or reversed? So means some actions can be reversed. The agent can backtrack And then he can go back. Like if we yesterday in the discussion we talked about the water jug problem, we are trying to solve it using BFS, where we tried and backtracked. Supposing if we try and choose a revisit step, we can go and go for the next thing. So similarly, can we go backtrack and try and find another solution? So these are the two key properties of problem formulation. Okay? Now, ignorable step. Let us go into deep and discuss about ignorable step. Okay, what is the key insight here? So, a step is ignorable if its omission doesn't prevent reaching the goal. So, agent may safely skip it without changing the outcome. Okay, so the outcome is going to be the same. So, what he must remember as a key insight? So, when a problem is decomposable, hmm, when a problem can be broken down into independent sub problems, solving one step doesn't dependent on other, because already we saw a lot of examples in the previous slides. Because each of the step is independent, so steps become independently ignorable. Okay, we took the example of Chennai to Delhi route planning example. So some intermediate cities can be bypassed if there is a direct route exists. So those steps are ignorable. Okay, so suppose there is a direct road from Chennai to Hyderabad, then the intermediate step of going to Bangalore can be skipped. So we can directly go to Hyderabad. So if the steps are ignorable, then the search algorithms can prune some of the branches. That's what we discussed in the example, right? I can skip the step of Bangalore. I can prune it. I don't have to go and waste my time there. So sometimes for the AI search algorithms, ignorable steps are a huge win because it saves your time, it saves your memory. Okay. So pruning certain steps or branches aggressively, so it will reduce your search space because the search space is very huge. It will reduce your search space. Okay. Next, we will talk about the recoverable steps. So these are the steps the agent can undo, undoable steps. Okay. Right. The step is recoverable if the agent can undo it, returning to the world to its prior state. So this enables backtracking when a wrong path is taken. Okay. So again, uh, you can take multiple examples of that. Like if you take the famous what is that problem? I have, if suppose if you're using the, like yesterday we discussed about the, like if you start from 0 comma 0, then I am at the second level of filling the 4-gallon jug, and then I am at the step of 3 comma 0. So handwriting is very bad, sorry. So when we try and explore these steps, and if one of the step is 0 comma 0, now I can ignore, I can go and backtrack and find another path because 0 comma 0 is already revisit. So the backtracking helps you in this undoing the steps. Okay, right. Alright. So multiple examples are there. Suppose in the exhaustive search examples like solving a chess or a puzzle. Okay, and then you can go always recover and undo the move and try for another search. For example, if you're trying to deal with a maze, okay, you go down to a corridor. If you're hitting a dead end, then you backtrack and find a different. Okay, the previous steps were reversible. Suppose we're taking chess simulations. So try a move virtually, evaluate the position, and then undo the same thing. Okay, so these are the reversible actions that can be done. Suppose if you take an example of a rocket launch. Okay, so once a rocket ignites, you cannot unlaunch it, right? So the step is irrecoverable. Irrecoverable. So every action must be perfect before execution because certain mistakes are permanent and costly. That's a challenging example, right? So We will talk about the comparison table here because we talked about ignorable steps, recoverable steps. Okay. Okay. Here, certain steps can be skipped. Let me take the highlighter for you. Okay. So, certain steps can be skipped safely. Certain can be undone or reversed, but cannot skip or undo. Okay. When you talk about the search strategy, you can decompose the problems and simplify it. Here you can use backtracking or either you can go for DFS. You have to have a careful forward planning. Rocket launch example. Okay. Here it is a route bypass we saw from Chennai to Delhi, where if you can directly go from Chennai to Hyderabad, you can bypass the Bangalore part. So chess move simulation can be done, virtual movements can be made. This rocket launch example we saw. So we cannot, this is an irrecoverable problem. Okay. When I talk about the state space, here simple, smaller, moderate, here is very, very complex. You cannot make mistakes. Risk is low, medium, and high because it's very, very permanent, very costly. When you talk about the algorithm, you can use greedy. Here you can use DFS with backtracking. You can use A star and careful BFS. So this is a comparison table. Okay. Now we will talk about the real world examples. Okay. So suppose if we talk about the navigation maps, okay, like Google Maps. So the intermediate waypoints can be skipped if a shorter path exists. So that's ignorable. A wrong turn can be corrected by rerouting it. Always multiple times we would have, I mean, we have used the Google Maps to navigate. So that's recoverable. Okay. So you can talk about game plannings, wherein certain moves can be pruned without losing the optimality. Okay. Simulated moves can be undone in a game tree. If you take a robot assembly, minor reportion steps can be skippable if some configurations, okay, some configurations are done, but physical assembly steps are often not recoverable. Okay, okay. The parts break, you cannot recover it, right? If you talk about medical treatment, okay, some diagnostic steps can be sufficient without prior information. Okay, that's ignorable. But many treatments are not reversible. Okay, so your critical planning is required there. Okay, if you're trying to take a chemotherapy or a surgery, you cannot undo these, right? If you started, you have to do it. You should be very, very careful. So now let's take a, I mean, we'll talk about this impact and then we'll go to the coding example. I have a code, sample code here. We will talk about that. Okay, right? So we talked, we will talk about the impact on all these search algorithms, and steps are ignorable, steps are recoverable, steps are neither. You have to use it carefully. Like we saw a lot of examples in the table itself. Like in this table itself, we made a lot of discussion. So when steps are ignorable, generally break it into independent subproblems, solve it in isolation, and then concatenate it. Okay. We saw a lot of examples. Suppose if you're assembling a machine, you can work separately and then you can collectively combine it. Steps are recoverable. You can undo bad steps and try the alternatives and visit better states so that your cost is low. You can use backtracking concept. Lastly, you must be very much deliberate. You cannot make a drastic mistake like rocket launch. Okay. Next, I will take an example. Okay. It's Python code. I only shown the portion of the code because it is very difficult for me to fit the entire code. So I've shown only the portion of the code. So this code will generally illustrate the recoverable steps. So it's a maze solver using the recursive backtracking. Okay, so this is a portion of the code. So we will try, since the maze, we will try and add the visited portions, and then we'll try what are the possible moves on the four directions, either through row or column. If necessary, we will try and backtrack it. So that is the code here. So I have shown you the same code I've told you. I have given an explanation so that you can just understand it. Okay. What we try to check, we will try and check whether the destination is reached. Okay. If not, you're going to add the current position to the solution path. Okay. Then every time we need to check if the current position is going to be the goal. Okay. Then you're going to return to, otherwise we try and append the current position to the solution path. Otherwise, we can say we are going to add it to the visited node or visited cell. So what we try and do here is we try and explore all possible directions. So what are the possible directions in a maze? You can move up, you can go down, you can turn left, you can turn right. So if one of the four directions lead to the goal recursively, then we can return true. That's a code tells here. Sorry, code tells here. Okay, right. So supposing if there is a path that is going to be incorrect, which might not lead you to the solution, then you're going to pop out that corresponding position from the path. So this is the backtracking. You're trying to undo operation. So this path might lead you to the dead end. So you're trying to move to another direction. Okay. You're going to go back and try for another. Now you can see here. So just one iteration. Okay. Now let's look at same code example only, but I've shown it for one where exactly you have to move. Okay. The starting position is here 0 comma 0. Like we can say like you're having like here 0, 1, 2, 3, 4. Similarly 0, 1, 2, 3, and 4. Your starting position here is here 0 comma 0. Okay. So initially you will append this path 0 comma 0 to the solution. You will add that to the visitor because you are in 0 comma 0. Now if you're going to, you have the options of moving up, down, left, and right. Okay. So you cannot move to these directions because X is a wall. Here also you have no place to move. So you have the only choice of moving down. So here it is false because you'll try to go outside the maze if you try to move upside. So you move down 1 comma 1 comma 0. So that's your position. That's a valid path. So this is a recursive call made. So the next position that you will go here is 1 comma 0. So likewise, from here you have to try whether you can move recursively. You have to try whether you can move left, up, down. Here also you cannot move. This is already visited. So again, you have to go down only, obviously, right? So likewise, you have to iterate over and over and over until you try and solve this complete puzzle. Okay, right? So next we'll move on to the next characteristics. Is the universe predictable? That is the third one. Okay, so this is about the environment the AI agent operates in. It's very important, right? We should know the environment in which the agent is working. So, what does predictable mean in AI? So, okay, so predictability means there are two key questions to answer. Can the agent always see the full state? Observability. We call this as observability. Whether the environment is fully observable. Second question is, do actions always lead to the same outcome? We call this as determinism. So, if S, the environment is deterministic, if it is fully observable and deterministic. So, if both answers are S, then we can say the environment or the universe is fully predictable. If either of this is no, then the agent must handle uncertainty. So there are a lot of examples on this. Okay, we'll talk about the types of environment in detail in future. Just for you to understand, for this fully observable environment, fully predictable, deterministic move. Okay, so if you take a traffic problem, that's not fully observable. First point, so it's no. You'll have uncertainties. Fully observable, like you can take XRO problem where you can in these many number of moves for sure you can attain the solution. Okay, right. So the types of environment in short, the environment can be fully observable plus deterministic, means fully predictable. The agent can see everything and every action and has a guaranteed outcome. So simple as 2 plus 2 is 4. That's not going to change. Right? This is the ideal case. Partially observable, the agent cannot see the full state of the world. It must maintain a belief state, a probability distribution over possible world of states. So it's very unpredictable. Okay. You can take a vacuum cleaner world if you are not knowing about where the dirt is. That's partially observable without the sensors. Right. Then if you talk about the non-deterministic environment, so actions might have multiple outcomes. Okay. Sliding a tile to cause another tile to shift. The agent must plan for contingencies, right? It's unpredictable. Which side you're going to move, left, right, top, bottom. Then both partial and non-deterministic. So it's very unpredictable, unreliable. Blind actions you have to do. So you have to have a sophisticated probabilistic planning for this, right? So these are the types of environment. We will talk about all these types of environment in detail in the rest of the chapters. Now let's take an example of 8 puzzle problem. Okay, so you know the 8 puzzle problem. It's a 3 cross 3 grid with 8 numbered tile, and we'll have one blank space. Work of the agent is to slide the tiles to reach the goal configuration. The goal might be any board position, like not any board position. You can keep the blank space anywhere, and you can say that is your goal. Okay? Now, let us answer a question like why is this? Before going and answering like why is this fully predictable? So we will talk about all these things, right? Right. So initial state, any scrambled arrangement of the tiles 1 to 8 plus your blank state, right? So you can make any scrambled arrangement of these tiles. Actions you can make is you can move the tile up, down, left, or right into the blank space wherever there is a blank. So the goal state is tiles arranged in order 1, 2, 3, 4, 5, 6. Like it should be like this. Tile arranged in order. I hope you understand that. Like 1, 2, 3, 4, 5, 6, 7, 8, and your blank. Okay. So you have so much number of states. You can see 1,81,440 states. So that is called as your state space. State space is all possible solutions, right? Next is your path cost, the number of moves taken to reach the goal. That's very, very important. If you're going to take one number of moves to reach the goal, there's no point. Okay. right? Now, we'll talk about why is this fully predictable? Okay, why is this 8 puzzle problem fully predictable? Because the agent can see all tiles at all times, fully observed. Okay, so nothing is hidden. Current state is always completely known. If I make this move, this is going to happen. It's already known. Secondly, it is deterministic. Sliding a tile always produces exactly one outcome. No randomness is there. The result of every action is 100% predictable. That's true, right? The static, the puzzle doesn't change on its own between agent actions. The environment waits for the agent, right, to make a move. Discrete, finite number of states and actions, because we know there are finite number of states and action. Nothing is continuous. We know totally what is a state space. 18144 reachable states. So what we try and conclude here is fully predictable universe. So you can apply the classical search algorithms like BFS, DFS and A star even using the heuristics to work on this particular problem. But why is it still hard? Even though we know it is fully predictable, why is it still hard? Look at the state space. It's very large. You have 181,440 reachable state. Okay. If you're going to use a brute force method, it's very, very expensive. Supposing if you're trying to use an uninformed search strategy, blind search like BFS, DFS, uniform cause search, anything if you're going to take, it's going to explode thousands of nodes, which is very, very expensive again. Right? So that is what we come into the concept of heuristics. So we need a good heuristics. So if we have a heuristics, it will guide you efficiently towards the goal. So what kind of heuristics can be used? You can try and find the misplaced tiles of the goal position. And then you can use the Manhattan distance, sum of distance each tile must travel. So you can use that. So these kind of heuristics can always help you to find or reach towards a solution. Supposing for this particular problem, if you're using BFS, so optimal solution is always there using BFS. But when you talk about the memory, already we know BFS consumes a lot of memory because it's going to go level by level. It has to store all the moves that it is making. But if you take a DFS, it's again efficient in memory. But if you go deeper, for example, if I have the solution, if you can attend the solution in level 5, suppose it's going to level 15, then you have to find a lot of non-optimal paths. So the best part here is we can try and use A star with admissible heuristics. It is the both optimal and efficient way. So it never overestimates. Okay. It tries to give you the answers efficiently. Okay. Supposing what if the eighth puzzle became unpredictable? Okay. Imagine the modified versions where the environment is no longer fully observable, means or predictable. Suppose if we have a partially observed version, some tiles are faced down, agent cannot see their values, like upside down, for example. So now it must maintain a belief state of the configurations. You know, there are so many configurations. Tracking all possible tile configurations that are consistent with what it can observe. Supposing if you're having a non-deterministic version, sometimes when you slide a tile, okay, And adjacent tile moves too. That is also there. So agent man must plan for multiple possible outcomes. Again, that's again challenge, right? So when you try to use hidden tile plus unreliable moves, then you have to use probabilistic planning for it. Very complex again. So key is the standard 8% problem solvable with classical search because the universe is predictable. The problem becomes fundamentally more difficult. Remove that, like the problem becomes more fundamentally difficult. Okay, like we'll take a small portion of the core of this. Here, what we're trying to do here, we're having a queue. Store states to be explored. For that, we have this queue. We try and dequeue every time you visit a tile. Okay, this is for avoiding the revisited tiles. Again and again, we cannot revisit, right? Okay, so it will prevent the revisiting of states. Then we'll check why the queue is not empty. We go and find the first state from the queue. We're going to remove the first state from the queue. That's what again queue dot pop left. And that particular state is it equal to the goal state. Then you're going to return the path. Otherwise, you're going to go generate all possible next states. Okay, right? Supposing if this explode states is not in the visited, you add one by one to the queue and then you try and visit it. This is a core code of the BFS. Okay. So this is the current blank tile position 1, 2, 3, 4. Here should be 5, 6, 7, 8. This blank should be here. Okay. This is considered as blank here. So possible moves here are, okay, I've given you like this. The new possible state might be 0 will go up like 103, 425, 786. This is one state. If I move this 8 up and 0 down here, 1, 2, 3, 4, 8, 5, and 706. Suppose if we move to the left, it's 1, 2, 3, 0, 4, 5, 7, 8, 6. If I'm going to move this right, 1, 2, 3, 4, 5, 0, 7, 8, 6. So these are the possible states. Okay. Next, we will move on to okay, the next characteristics is a good solution, absolute or relative. Okay. This is for this portion. This is the last characteristics. In the next portion, again, we will talk about the other characteristics. So, when the agent finds a solution, is that solution absolutely optimal or just relatively good? Okay. So, is there one single best solution that is universally correct for a given problem? So, the solution is optimal by a fixed objective standard. Okay. So, we have to find that is there something that's precise, there is a precise cost function, and our solution minimizes it. If there is no solution, tries to minimizes it, that is absolute. When you talk about is it relatively good, is a solution good compared to other available solution alternatives? Given the constraints very hard, is there any other solution for it, available solution? So it necessarily not need to be optimal, but at least satisfying, good enough, something like that. So we have to find that. But the answer depend upon how the problem is formulated. So what is the path cost? How the goals are defined? Okay. So based on this, your solution might be, and it might give you an answer whether the given solution is absolute or relative. These things are dependent on that. Okay. Now we will talk about different types of solution. A solution is a sequence of actions leading from initial state to the goal state. That is the classical search. In a classical search, that is what is called as a solution. Now we'll talk about different types of solution. The first one is the any solution. So first one, just reach the goal. Quality does not matter. Just like finding an exit from a maze. Okay, just finding any path. It need not be optimal. That is any solution. Next is an optimal solution. So reaching the goal with minimum cost. Okay. So the shortest path, finding the shortest path in the maze. Next one is a satisfying solution. So it should meet a minimum threshold. So might be we can say you should find the path in the maze in under 10 steps. Just shorten it. So these are the different types of solutions. Okay. Now we'll talk about the same thing. We'll just when I talk about a solution, solutions are absolute when there is a clear, measurable, objective cost function. The agent tries to minimize it. That is, there is only one best answer. Supposing, okay, for example, if you take a path fixed cost function. So path cost is definitely defined precisely. Number of moves, what is the distance between one city to another city, how much time it takes from moving from one city to another city. Okay. So we have to try and find the best solution that has the lowest possible cost. Okay. So we have already discussed an example of moving from Chennai to Delhi. Okay. So we'll have to find the shortest, that is the best solution. You can take one more example, 8 puzzle problem. So we have to find a minimum number of moves to reach the goal state. Okay. If you try to find a solution with 20 moves, it's worse than one with 15 moves. You cannot take that. Right. So algorithm that finds the absolute solutions include BFS, also uniform cost search, A star search with admissible heuristics, and uniform cost search. Okay, so if I talk about all these things, I can say a solution is absolute when there is a clear, measurable, objective cost function. So the agent will try to minimize it. That's what I've tried to understand here. Okay, I will talk about relative solutions. So we were talking about absolute solutions. Now we will talk about relative solution. A solution is relative, okay, when good depends on text, on context, constraints, available resources, or comparison to alternative. Right, sometimes optimal solutions are too expensive, then we can go for relative solutions. Consider the time constraint. Suppose if you're taking up a navigation app, it needs to give you directions in 1 second. So it cannot afford you to explore all possible states. For example, if you have 1,81,000 and odd states for that particular road network. So if there is a proper available heuristics, then it will try and find out the easy or the quick shortest path for you. Okay, the heuristics based will try and find you the shortest path. If you take the greedy best first search, it finds a solution very fast. But when we talk about the optimality, it's not good. Okay. If you talk about the real world scheduling, logistics, and planning, finding the globally perfect solution is computationally intractable. So, a near optimal solution within the goal is practical and correct. Okay. So, algorithms for relative solutions include greedy search, hill climbing, simulated annealing, and genetic algorithms. Okay. Now, this slide will show a table of how the definition of good changes with respect to Hathka's definition and then what good means exactly. Okay. If the good equals number of steps, okay, fewer smooth wins. If it is, if the cost equals distance traveled, then shortest route wins. If it is time based, then the fastest route wins. With financial cost, cheapest wins. That's equal to the best. If we talk about risk factor with respect to good, safest wins. Okay. Supposing if you're talking with weighted combinations, then multi-objective is best. Supposing if no cost is defined at all, then that any solution is good. Just reaching the goal is enough. Okay. So this is what the path cost with respect to good. Okay. Now we will talk about one example with the known facts. This will this example actually will help you to understand the difference between absolute conclusions and relative solution paths. So the facts are given here. Marcus was a man. Marcus was a Pompeian. Marcus was born in 40 AD. All men are mortal. It is now 2024 AD. All Pompeians died when Vesuvius erupted in 79 AD. No mortals live longer than 150 years. So the question here is Marcus alive? Okay. So with all these known facts, I have to conclude that whether Marcus is alive or not. Okay. So the answer is, or the answer the agent must derive is Marcus is not alive. This absolute. So every valid reasoning path leads to the same conclusion. Yes. Okay. The truth does not change. See, we know the sun rises always in the east and sun sets in the east. I'm asking a question like, today, did the sun rise in the east? You will always conclude the sun rises in the east. Okay. We know now we understood like the solution is absolute here with the known facts. So there are three paths. Path one, via Pompey. Marcus was a Pompeian, all Pompeians died, so Marcus is dead. Via mortality. Marcus was a man, all men are mortal, no mortal lives past 150 years, it's 2024 years, so this is dead. Longer chain uses general rules. Both path combines all agent uses all facts and reaches the same conclusion. Okay. The destination is the same, the path differs in length, facts used, and robustness. So, this is the essence of absolute versus relative solutions. Okay. So, To conclude, like I've just put it in the table for you. Mock test is not live is absolute, but the solution path is relative. That's what you have to understand. Every valid reasoning path leads to the same answer. The truth does not change. If we talk about all these steps, facts, use, robustness, cost with respect to the three paths, when we talk about path 1 through Pompeii, the steps is fewer, facts use is specific, robustness is just fragile and depends on one fact, and the cost is very low. If I go with the path 2, that is mortality, the number of steps involved is more, facts uses general facts, robustness uses general rules, and the cost is medium. When I combine these two, most of the steps you have to use, all facts you have to consider, most robust, and the cost is also very, very high. Okay. So, good solution in AI is not inherently about absolute or related. So, it depends entirely on how the path, cost, and the goals are defined in the problem formulation. We have discussed a lot about this. If you have an optimal solution, that is, absolute solution exists when a precise, objective, and cost function is defined and the algorithm is designed to minimize it. Also, we have seen relative solutions are used when optimal search is too expensive and the time is limited, or if it is good enough to meet the real world requirement. That's very important, right? Every time you cannot depend on the optimal solution, right? So the key takeaways here, first we talked about the decomposability, whether is a problem decomposable or not. We saw a lot of examples. We took the the root map, blocks world problem, and we saw the chess is a non-decomposable problem. Then we talked about ignorable and recoverable steps, okay, so that we can prune certain branches. We talked about DFS with backtracking. Thirdly, we talked about predictability, fully observable plus deterministic equals fully predictability. We took the 8 puzzle example as a problem. And then fourthly, we discussed about absolute versus relative solutions. We discussed a lot about that. So closing, the four characteristics are not just theoretical. Every time an AI engineer designs a system, example, a navigation app, a game playing AI, a medical diagnosis tool, all these are implicitly available there. These questions are always being asked. So, understanding the problem characteristics guides every design decision. Okay. So, what kind of representation you're going to use, what kind of algorithm you're going to apply for this, what is the quality of the solution. Okay. So, we have remaining characteristics to be discussed that I will do it in the as a part 2. Okay. Now, the references used are Stuart Russell, Peter Norvig, Parag Kulkarni, and Elaine Rich. Thank you for listening.